In this lesson, let's learn about the necessary and sufficient conditions together. We know that logic is closely related to our lives, and we are always unconsciously using logic in our daily lives. It can be said that logic makes our lives orderly and makes us better at learning and thinking. Today, let's learn about the sufficient and necessary conditions together. Before studying, let's first review a concept: proposition. In junior high school, we already had a preliminary understanding of proposition. Generally, we call a statement expressed in language, symbols, or formulas that can be used to determine its truth or falsehood a proposition. Statements judged true are true propositions, while statements judged false are false propositions. In high school mathematics, many propositions can be written in the form of if P, then Q. For example, can students rewrite the proposition of equal vertex angles into the form of if P, then Q? The answer is if two angles are opposite vertices, then these two angles are equal. The former is condition P, and the latter is the conclusion Q of the proposition. Obviously, this is a true proposition, and P can deduce Q. So, what is the relationship between P and Q at this point? In this lesson, we will study two commonly used logical languages in mathematics by studying propositions in the form of if P is Q, adequate and necessary conditions. We define that if P then Q is a true proposition, which means that P can deduce Q through reasoning. At this point, we say that P can deduce Q, denoted as P deducing Q, and that P is a sufficient condition for Q, while Q is a necessary condition for P. That is to say, two angles are opposite vertex angles is a sufficient condition for two angles are equal, while two angles are equal is a necessary condition for two angles are opposite vertex angles. Some students may have questions. Why is it named like this? Sufficient means sufficient, and the condition that two angles are vertex angles is sufficient to derive the conclusion that two angles are equal. Necessary means essential. If you want two angles to be vertex angles, you must first ensure that they are equal. If two angles are not equal, they cannot be vertex angles at all. At the same time, if we say that if P, then Q is a false proposition, then the conclusion Q cannot be derived from the condition P, denoted as P cannot derive Q. At this point, we say that P is not a sufficient condition for Q, and Q is not a necessary condition for P. So when we get a proposition in the form of if P, then Q, are there any techniques to quickly determine who is who and what conditions? We can judge by the direction of the arrow. The arrow points to the necessary conditions, and the tail of the arrow points to the sufficient condition. Let's consolidate our knowledge through examples. We see example 1. Which of the following 6 propositions has P as a sufficient condition for Q? Please think about the sufficient condition for P to be Q, which means who derived whom. It should be P that leads to Q, so we only need to analyze one by one whether P can lead to Q. Can we infer that this quadrilateral is a parallelogram from the statement the two diagonals of the quadrilateral are equal? Obviously, it is possible because this is a theorem for determining parallelograms. Therefore, P can derive Q, and we say that P is a sufficient condition for Q. Can the statement the three sides of two triangles are proportional lead to these two triangles are similar? Similarly, this is a theorem for determining similar triangles, where P can derive Q. We say that P is a sufficient condition for Q. Can we infer that the diagonals of a quadrilateral are perpendicular to each other? Obviously, because this is the property theorem of diamonds. P can derive Q. We say P is a sufficient condition for Q. Let's take a look at the fourth one. Can we deduce that x equals 1? By solving the equation, it can be concluded that the solution where the square of x equals 1 is 1 and minus 1. That is to say, if the square of x equals 1, it does not necessarily mean that x equals 1. Therefore, P cannot derive Q, and we say that P is not a sufficient condition for Q. Looking at the fifth one again, can A equals B lead to AC equals BC? It can be inferred from the properties of the equation that it is possible. So P can deduce Q. We say that P is a sufficient condition for Q. Can we deduce that x multiplied by y is an irrational number? It is easy to find that the root 2 is an irrational number, but the product of 2 roots 2 is a rational number too. So P cannot derive Q. We say that P is not a sufficient condition for Q. From here, we can see that giving counterexamples is an important method to determine whether a proposition is false. So in the 6 propositions of example 1, P in 1, 2, 3, and 5 is a sufficient condition for Q. Now, please consider the following question. In example 1, proposition 1 provides a sufficient condition for a quadrilateral to be a parallelogram. That is, the two diagonals of the quadrilateral are equal. Is this sufficient condition unique? If not unique, can you provide several different sufficient conditions? Obviously, such conditions are not unique. Why don't you press the pause button and think for 2 minutes? Write down everything you can think of. Okay, let's talk about it together. According to the definition and techniques, we need to find sufficient conditions for a quadrilateral to be a parallelogram. That is, we need to find conditions that can lead to the statement a quadrilateral is a parallelogram. What other conditions can we meet? For example, the two opposite sides of a quadrilateral are parallel to each other. The two opposite sides of a quadrilateral are equal. A set of opposite sides of a quadrilateral that are parallel and equal. The diagonals are evenly divided among each other, and so on. In fact, it is not difficult to find that the above propositions are all judgment theorems for parallelograms. That is to say, each decision theorem of a parallelogram provides a sufficient condition for a quadrilateral to be a parallelogram. This condition can fully ensure that the quadrilateral is a parallelogram. Therefore, we can draw the first conclusion. Generally, every decision theorem in mathematics provides a sufficient condition for the corresponding mathematical conclusion to hold. May I ask if you can provide examples to illustrate the above conclusion? Please think carefully. For example, every judgment theorem for parallel lines provides a sufficient condition for two lines to be parallel, such as equal misalignment angles, equal same position angles, complementary same side interior angles, and so on. Let's take another look at example 2. Which of the following 6 propositions is a necessary condition for Q to be P? Please think carefully again. Now we need to ask who is the necessary condition for Q to be P, and who introduces whom. According to the definition, P still deduces Q, so we only need to analyze one by one whether P can deduce Q. Can the first question, a quadrilateral is a parallelogram, lead to the two diagonal angles of this quadrilateral are equal? Obviously, it is possible because this is a property theorem for parallelograms. So P can deduce Q. We say Q is a necessary condition for P. Can the second question, two triangles are similar, lead to the three sides of these two triangles are proportional? Similarly, this is a property theorem for similar triangles, where P can lead to Q. We say Q is a necessary condition for P. Can the third question, the diagonals of a quadrilateral are perpendicular to each other, lead to the statement this quadrilateral is a diamond shape? As shown in the figure, the diagonals of this quadrilateral are perpendicular to each other, but it is not a diamond shape. Therefore, P cannot derive Q. We say Q is not a necessary condition for P. Let's take a look at the fourth question again. Can we derive the equation x squared equals 1 from x equals 1? At this point, we only need to input x equal to 1 into the equation, which obviously holds true. So P can deduce Q. We say Q is a necessary condition for P. Looking at the fifth question again, can AC equals BC lead to A equals B? Obviously, if C is 0, then regardless of whether A and B are not equal, we have AC equal to BC. Therefore, P cannot derive Q. We say Q is not a necessary condition for P. Can we deduce that x and y are irrational numbers from the final question x multiplied by y is a rational number? For example, multiplying 1 by the root 2 equals the root 2, which is an irrational number. However, it is clear that both 1 and the root 2 are not irrational numbers, so P cannot derive Q. We say Q is not a necessary condition for P. So among the 6 propositions in example 2, only Q in 1, 2, and 4 is a necessary condition for P. Now please consider the following question. In example 2, proposition 1 provides a necessary condition for a quadrilateral to be a parallelogram. That is, the two diagonals of the quadrilateral are equal. Is this necessary condition unique? If not unique, can you provide a few different necessary conditions? Obviously, such conditions are not unique either. Everyone can press the pause button again and think for 2 minutes. Write down what you have in mind. Okay, let's talk together. According to the definition and techniques, it is necessary to find the condition that a quadrilateral is a parallelogram. That is, to find the condition that a quadrilateral is a parallelogram can still be derived. For example, the two opposite sides of a quadrilateral are parallel to each other. The two opposite sides of a quadrilateral are equal. A set of opposite sides of a quadrilateral that are parallel and equal. Diagonal lines can be evenly divided, and so on. Obviously, the above propositions are actually property theorems of parallelograms. That is to say, each property theorem of a parallelogram provides the necessary conditions for a quadrilateral to be a parallelogram. For example, if the two opposite sides of a quadrilateral are not equal, it cannot be a parallelogram. Therefore, we can draw the second conclusion. Generally, every property theorem in mathematics provides a necessary condition for the corresponding mathematical conclusion to hold. May I ask if you can provide examples to illustrate the above conclusion? Everyone think carefully. Similarly, each property theorem of parallel lines provides a necessary condition for two lines to be parallel, such as equal misalignment angles, equal same position angles, complementary same side interior angles, etc. It can be said that if the misalignment angles are not equal, it is impossible for two lines to be parallel. Finally, let's summarize the main learning content of this lesson. In this lesson, we mainly learned two commonly used logical expressions, sufficient conditions and necessary conditions. Secondly, we have clarified the technique of determining sufficient and necessary conditions, that is, to see who deduces whom, that is, to look at the direction of the arrow. If P can deduce Q, we say P is a sufficient condition for Q, and Q is a necessary condition for P. Thirdly, the relationship between sufficient conditions and judgment theorems, necessary conditions and property theorems has been clarified. Each judgment theorem provides a sufficient condition for the corresponding mathematical conclusion to hold, while each property theorem provides a necessary condition for the corresponding mathematical conclusion to hold.